2 centimeters to the left or right.
Okay, good morning. So let us start this lesson. Okay, so this lesson is more or less very familiar, hopefully, for you from your high school studies. It might be we will a little bit complicated from theoretical point of view. So the idea is that if you want to have a good qualitative graph, so you need some mathematical tool. Yes, for example, if I ask you to draw the graph of y equals to x squared, if you want to do it in the rough way, of course what you do, you pick up some points and highlight them on the display, but of course you are not allowed to connect them. You have to in principle highlight all possible points that are introduced by this, which is impossible to do. So for example, if I put x equals to 0, I get y equals to 0, so this highlights this point, and if I put 1, x1, y also becomes 1, it highlights that point, and then if I put minus 1, it becomes 1 again, it highlights that point. Of course, I want you to feel that in principle I am not allowed to connect the points, so I have to highlight all possible points, and what I get at the end is called the graph of the function. And this is usually impossible because the domain of the function contains infinitely many points. Okay, and then of course you might say, okay, if I pick another point 1/2, then I get a quarter, so then I can estimate the graph of the function. You might say that I can connect them in this way, it is a good approximation to the graph of the function, but technically speaking that is not correct. You know, because it doesn't matter how many points I put in, I get better and better approximation, but there is no guarantee what is going to happen between these 2 points. So who knows? Of course, this is so famous and you have been working with this for your life now, so you know that the graph of the function looks like this. But in principle, if the function is complicated and you don't have any clue about the final picture, so this is potentially possible that this function, for example, from here to here doesn't go in that way, but goes in the other way. And this is qualitatively different. People can detect the difference between these. I just want to mention that we need some kind of analytic tool in our hand to be able to have a good qualitative picture of the graph of a function at the end. Yes? So even if you have computer available, so when you draw the graph of this function, your monitor is limited. So, for example, the application gives you the graph of the function, but you need to know if this is the whole story of the graph. Who knows that if I go to the right a little bit up or down left, I will not get some kind of new surprises that it will change the picture of the graph at the end. So at least I hope that you understand that we really need an analytic way to be able to understand the qualitative form of the graph of a function. Yes? Is that clear? Okay, now if I draw any function for you like this, I don't know, because we are humans, I am counting on your human intuition. So if I draw a graph like this, let us say that this is the graph of my function. Of course, all the points on the graph are important, but hopefully you see some points are more important than the other ones. So which one you prefer to? So which one do you think are more important than the other ones? These bumps, yes, these up and downs, yes. So yeah, this is why we want to have a definition for them to see if we can find these points, because now if I know this, so if I somehow manage to find this, then I know that at this point the graph will turn down, and at this point the graph will turn out, will turn up. So these points are important. Okay. So this is what I just want to motivate you why for the first part of this lesson we are interested in what we are doing. So we want to give some names to these bumps. So what are these? So then we can try to find an analytic way to determine. Okay, so as you see in this picture, of course I don't know why they haven't included something else here. So if you see this picture, we want to have a definition for these turning points. Okay, so let me draw something for you there on the board. Might be it is a little bit better. So there are some points that terminologies that we want to learn about them. So let us say that I start from some point, I go up, and then I come like this, and then I can, for example, come like that, and then go sort of, and then this something might happen like this, then I go up, and I go down, and I go up. Something like this. Okay, so let me call this point A, I don't know, this one x1, this one x2. For the time being, I'm considering continuous function. So I don't know if I could draw it carefully, but let me also give this a name 3, and this one 4, and this one, if I can draw it a little bit better, x4, x5, and let me call this.
There are 2 x4s.
Oh, sorry, x5, x6. Okay, thank you. Okay, so first of all, I want to talk about what do I mean by a local maximum point. Okay, so there are some terminologies. Endpoints are clear, yes? And A and B are the endpoints of this graph. So what is the local maximum? A local maximum is a point so that its height is more than the height of the points in a neighborhood, no matter how small the neighborhood is. So this means that, for example, this point, the height of this point is not the highest point of the graph. For example, you can see the highest point is there. But compared to the points in the neighborhood of this point, so you see that this is higher. If this happens, we say that this is a local maximum. So a local maximum is a point on the graph so that you can find a neighborhood around that point, no matter how that neighborhood is small, how small that neighborhood is. The height of that particular point compared to the height of the points in that neighborhood is higher. That is called the local maximum. So, okay? So, and then this one is a local minimum. Okay, so in this case, yeah, you see that this is not the minimum. This is because here is lower. But this is locally minimal. Yes, it means that the height of this point is lower than the height of the points in the vicinity of that point, in the neighborhood of that point. Okay, so that's it. So that is the local maximum, and that's the local minimum. Now the point is that, the logic is that you don't have access to the graph of the function. The formula of the function is given to you, and you want to really calculate this point x1, x2, etc. So you want to determine them without having access to the graph of the function. Okay, so we have to understand what are the similarities. For example, if I want to look for this point on the graph, I hope that you can see that it is pointless to look everywhere. I need to look at those points whose the tangent to the graph exists and is horizontal. So if I take the derivative and put it equal to 0, what might I get is this point. Or might be I also get this point. Yes, because there it's also horizontal. The tangent is horizontal. So if I take the derivative and equate it to 0, the answers that I get, this one is among them. Yes, because the tangent is horizontal. This one is also among them. This is also horizontal. And of course, if I could draw it carefully, this one is also among them. And this one is also among them. Yes? So if I take the derivative and equate it to 0, you immediately see that there is no guarantee that I can find the coordinates for the local minimum and the local maximum. Local minimum points and local maximum points of this type are among them, but there might be some fake ones also coming in, which I'm not interested. This is not a local minimum point. Yes, do you see that? Because this point is higher than the points on the left, but it is lower than the points on the right. So it is neither a local maximum nor a local minimum. The same is true for this one. So we have to find a way to differentiate between them. Okay, so what is the difference between these behaviors? So here, the function increases before the point and decreases immediately after the point. So this behavior, going up and coming back, is an indication that I have a local maximum. Yes, what about this one? This one first goes down, on the left it goes down, and immediately after that it goes up. So this one indicates a local minimum. Okay, But this point, which is called an inflection point, or if you have done it in high schools in Sweden, they call it terrace point, because they differentiate it between a terrace point and an inflection point. Terrace point is a particular case of an inflection point, but no worries here. So you can see that what is the behavior here, what is the behavior here. The behavior here is that the function before that is increasing, but it continues to increase even on the right side. So you have this behavior on both sides. So this means that this is some kind of an inflection point. We talk about inflection point. For the time being, let me call it a terrace point. It's not a bad terminology. A terrace point is a point that is not a local maximum or local minimum, but the first derivative exists and it is equal to 0. And it is not a local minimum and local maximum. Okay? So this one, before that it goes down, after that it also continues to go down. So you can differentiate the behavior at a local maximum and a local minimum and a terrace point by investigating if the function is increasing or decreasing on the other sides, on both sides of this point. Is that clear? So the high school study stops here, but you see that there are some other points here. So if I see that this is a local minimum, you agree this is a local minimum and that's a local maximum, but these 2 points cannot be derived from the previous method. Do you see that? Why? Because in the first method, I take the derivative, I differentiate, put it equal to 0, and then find the answers. So it means that I am assuming that the derivative exists and it is equal to 0. But at these 2 points, even though it's a local minimum and it's a local maximum, the derivative does not exist, because what we learned before, that's a sharp point. And at these points, the derivative does not exist. But still, here I have a local minimum and here I have a local maximum. So if I just limit myself to take the derivative and put it equal to 0, I get some candidates for this, for this, for this, for that, but I will never get a candidate for this one and that one. Is that clear? But if somehow I can manage to find x2 and x4, still the behavior is the same. How can I understand that which one is local minimum, which one is local maximum? The same idea. Before a local minimum, the function is decreasing. After the local minimum, the function is increasing. The same for this. So that part of the behavior is the same. Okay, so how can so if now this picture is important because I want to summarize an algorithm for you. So let us ask you, okay, by the way, in your book, they are also considering this endpoint as a local min. So this is the definition that your book uses, and I will try to adapt myself. What does it mean? It means on the left-hand side, I don't see anything. But it is not a bad convention, because now, if I limit myself to the neighborhood around that point, of course on the left I don't have anything, on the right I have one-sided neighborhood, and this point is lower than the points up in the neighborhood. So in the book, this is also called a local minimum. And for example, what do you think about this? So even if I draw it like that, so don't give that bump to it. So what do you say about that?
Local maximum.
That's a local maximum according to the definition in your book, yes.
If we include all points but not the point B, is there a local maximum at B?
No, because that point is not on the graph.
And you can't pick any other point.
No,
That is
yes,
B.
yes,
Okay.
yeah. Okay, but now can you come up, my goal is that, by this try to give you the motivation, my goal is this. Someone gives me a function, not the graph of the function, someone gives the formula for the function, and my duty is to find all these points, local maximum points, local minimum points, terrace points, and everything. And I want to also know which one is which. Which one is minimum, which one is maximum, which one is terrace point. So can you come up with an algorithm yourself? So if you want to do it step by step, so a function is given to me, and I want to locate all points, and I want to specify the character of the point. Which one is minimum, which one is maximum, which one is terrace. So how do you do that? Yes?
We can take the function and we can find the derivative, set that equal to 0, and find the values of x. That will give us the...
This gives me these candidates, yes?
And the terrace points as well, yeah.
Yes, this will give me these candidates.
But to differentiate, we can notice that the derivative before and after, let's say.
But what's
for
not
local
finished?
minimum.
I need also tell me how should I find other candidates.
Yeah, that's what I'm getting on.
Yes?
So when we set it equal to 0, we find the local minimum, maximum, and terrace points.
Candidates for that.
Yes.
Yes.
Now to differentiate between them as to which is terrace points and which ones are the local minimums and maximums, we can sort of notice that the derivative before and after, say, a local minimum maximum is positive and 0.
Yeah.
So if we plot the graph of the derivative, you can see that at that specific point, if it's a local minimum or maximum, the x-intercept is 0. Right?
X-intercept, what do you mean?
It's like, so it,
No, my question for you is that, okay, I understand, you located these points and you
Yeah.
want to recognize which one is which.
It's
But now my
2%.
question is more than that. Before recognizing the character of the points that you found as a candidate, my question is that how can I proceed and find other candidates? Yes, please?
Well, first I need to find all the points where the derivative is 0 and where the derivative is undefined. And then
Does not exist, yes, undefined. So this will give me, so yes, the first one you said is right. We take the derivative and we consider two different types of points. The points at which derivative is 0, it will highlight these candidates for me, and the ones that the derivative is not defined or does not exist will highlight these points, and according to the standard in the book,
And the edge cases.
and the endpoints. Okay? So these are the only possibilities. Then, of course, what you are talking about is increasing, decreasing behavior is correct. Yes. So is that clear? So I don't want you to memorize the algorithm because there will be different algorithms probably coming in and then you will be confused. So if your goal is to locate all maximum and minimum points, what you do, you take the derivative and put it equal to 0. You get a bunch of points. In this case, which points I will get? I will get, for example, x1, yes, and I will get x3, x5, and x6. x1, x3, x5, and x6. Am I right? I will get these ones if I put it equal to 0. And then I calculate the derivative does not exist. I demand it does not exist. Doesn't exist. Then which points I will get? I will get x2 and x4. And then finally endpoints, which are A and B. Yes? So in this way, I will find all possible candidates that I want. And then of course, what you said is correct. If I have a local minimum, if I have a local maximum, the derivative, the function is increasing. What does it mean? It means the derivative on the left is positive, and the derivative on the right is negative. It doesn't matter if it is of this type maximum or it is of this type maximum. Both of them are the same. And for terrace points, the increasing, decreasing behavior does not change before and after. And for a local minimum, this is the other way around. What about the endpoints, by the way? If the endpoint is a local minimum, on the right-hand side, the function is increasing. If this one is a maximum, on the left-hand side, you see the function is also increasing. Okay, and there are some terminologies. In your book, these points are called critical points. Critical points. These points are called singular points. Yes, so these are the terminologies you need to know. But something is important. They also should belong to the domain of your function. If it is not, we don't call it critical or we don't call it singular. So is that clear? So this is more or less what I have written in the first page. For example, let us just go. And by the way, what we talked about, that if the function is increasing before and decreasing after, and the other way around, it gives you local maximum, local minimum, is the content of what we call the first derivative test. So that is the first derivative test, which is very obvious actually, very intuitively clear on this page. Okay, so for example, if you don't mind, let me start with example 2. number 2, because number 1 is very simple, it's mainly from high school. So I give you this function. Example 2, part 2. X to power 4 over 3 plus I have 4 x to power 1 over 3. Yes? And this is the question. The question is that determine the extreme points. By the way, if I say extreme points, I mean both minimum and maximum points. So determine the extreme points of this function and specify the nature of these points. Okay, so let us do it. The first thing that usually you should do is the domain of the function. You should have an idea of the domain of the function, because domain also matters because of the endpoints. So can you tell me what is the domain of this function? Yes, because this is the third root, and for the third root I don't have any restriction, so the domain of this function is the set of all. So, and now what I will do, I will actually differentiate my function. So 4 over 3 goes down, then I have x to power 1 over 3, and then 1 over 3 goes down, which gives me 4 over 3 again, x to power minus 2/3. Yes, this is the derivative of my function. I would recommend you to simplify it if possible. So for example, you see that I can factor 4 over 3 out, then I am more comfortable to work with third signs, these radical signs. So this is the third root of x, and I prefer not to work with negative exponents. I bring it down so it becomes positive, but then I can write it as the third root of x squared. Do you agree? And because in the future I want to determine the sign of the derivative, because I want to know if the derivative is positive or negative, I prefer not to write it as a sum. I prefer to write it as a product or a fraction, because determining the sign in that form would be suitable or easier. So this is why I take the common denominator. So I have 4 over 3, then I have the third root of x squared. This one multiplies itself here, it gives me the third root of x cubed, which is x, and this hasn't changed, it hasn't changed, so it gives me this one. So hopefully you agree with me, this is your simplified derivative. Okay? Now, the first part of the algorithm tells me find critical points. Critical points are the points for which the derivative exists and is equal to 0. But of course, the points should also belong to the domain. Be careful about that. So for example, if I put f prime of x equals to 0, so let me write it more. So for critical points now, so critical points, so it means that I put the derivative equal to 0 and try to solve it and find all of them. So this means that 4 over 3 x plus 1 over the third root of x squared is equal to 0. So what is the answer now? I want this fraction to be 0, so its numerator should be 0, and x becomes equal to minus 1. But I just want to make sure that you be careful. Sometimes you get something which is not in the domain. Of course, here the domain is R, so you don't need to be sensitive about that, but you have always to check if this is in your domain or not. Yes, it is, so this is the only critical point I have. Yes? But now, I need another type of points. The function, the derivative does not exist. The points of singularity. So singular points. So this means that f prime of x does not exist. So can you tell me what is the only candidate here? This is my derivative. I might demand this to do something that this does not exist. So what is that number? 0, because the denominator should be equal to 0. So this means that x should be equal to 0. Again, before accepting it, you have to compare it with the domain. Of course, in this case, domain is R, so it is acceptable. And what is the next one? The next candidate is endpoints. So there are no endpoints here because I am working on R from minus infinity to infinity. So domain of F is R. This there are no. There is no endpoint. Yes. Okay. So these are my candidates. So now what should I do? So I want to use the first derivative test, okay? The first derivative test. So the first derivative test, you can actually draw some table. So x goes from minus infinity to infinity because I don't have any limitations of the values that I can choose for x. But I have two candidates. One of them is 0, which is of the type singularity, singular point, and this one is critical point. But this one is a smaller, so I put the smaller on the left and the one here on the right. Okay, so I don't know how you want to write it, and usually this is the convention. The middle row is f prime and the last row is f. Okay, so at this point, the derivative is 0. At this point, it is undefined. Yes. So here, if you want, you can calculate here, but let us skip that one. So what you do, you take it with you if you really want to know the y coordinate. Then you put it in your original function because this is the f row. So don't get confused. You have f prime and f, but this is the f row. So if I want to know that number, instead of x, I put minus 1. But minus 1 to power 4 is positive. This is it's minus 3. If you want, we can calculate, but this is not necessary for this exercise. And what about 0? If I plug 0 here, I also get 0 back. Okay? And now we want to know if the derivative is positive or negative. So that is the final form of your derivative, which is important for you. For positiveness or negativeness, you can ignore 4 over 3 because it doesn't change anything. And then I have a fraction. So you see it is not that hard. If you choose a number less than minus 1, what happens to your numerator? It becomes a negative number. But the denominator, because of that even power, is always positive. So when you divide, it becomes negative. And now you are somewhere between minus 1 and 0. So what happens? If you pick a number between minus 1 and 0, any number, not a number, any number between minus 1 and 0, this becomes positive, and the denominator is again positive. So this is also positive. At 1.0, the derivative is not defined, but on the right-hand side of 0, the derivative is again defined. What is the sign of it? Positive. So that's also a positive. Yes? So then what happens? Here, the function is decreasing. Here, the function is increasing. Here, also the function is increasing. Okay? So this behavior, you can see that. So this minus 1. By the way, I don't know why this, I'm not used to it, but the convention in the book, they call minus 1 the point, which is a little bit strange, yes? They say at the point minus 1. But usually when we say a point, we have both x and y coordinates. So don't get confused about these things. So I prefer to say that minus 1 and minus 3, which is a point on my graph, is a local minimum, okay? But in your book, they say minus 1 is the minimum point, and they say the value of the minimum is minus 3. That one is correct, but the point I used to write it. Anyway, x minus 1, you write it local minimum. What do you think about the other candidate? What type of point is that?
Inflection.
It is an inflection, but is it of this type or not?
No.
It is not of this type. How do you know? Because inflection points of this type, which we call the terrace points, are the ones at which derivative is equal to 0. Okay? But here the derivative is not defined. Okay? So somehow it means that the function, if you want to have an idea, and by the way, can you tell me what is Do you think we have a tangent line there at 0, 0 to the graph?
Yeah.
Because if I put 0 here, it means the derivative is somehow infinity, and it doesn't matter if I am on the left side of 0 or the right side of 0. This is always positive infinity. So in principle, if I am right, you don't need to draw it here, but if this point is minus 1 and 3, this is a local minimum point, yes, and then the graph passes through 0 and 0, but at that point, the behavior before and after is increasing, and the derivative is somehow infinity at that point. So it means the tangent should be a vertical tangent. So somehow it should be like this. Something like this qualitatively. Yes? Any questions? So this is the setup that you need to know. You take the derivative simplified as much as you can, critical points, singular points, end points, and then set up this sign table. We call it sign table, yes. Sign table, and then recognize which one is which. Is that understandable? Yes?
So what do we put? We don't describe the point at all.
This one?
Yeah, we don't.
Now you can say that this point in the future, we haven't talked about inflection points yet, but you can say that this is an inflection point of this type. Yes. Any questions? Okay. Let me jump to number 4, because number 4, this is also not something we learned in high school studies. This is a function with more than one root. Okay. So the same example, but number 4. So f of x is given to be this two-ruled function, yes? X squared 2x if x is less than or equal to 2, and then x to power 3 minus 18x plus 28 if x is greater than 2. And the question is the same question. So we want to locate all possible local max, local min points. Okay. And by the way, let me tell you something, because if we are talking about the first derivative test only works for the continuous functions. Because if we allow this continuity to come in, then we have very weird conditions if that is a very severe discontinuity. For example, can you see what happens here? I draw the function like this, I make this hollow, I go up, and then I put it up to here. So you see if this point is A, and this point is f of A, and if this is the graph of my function, what this point is?
It's a maximum local.
It's a local maximum, yes, but you see it behaves as if it's a local minimum, because the function before this point is decreasing, and immediately after that point is also increasing. But exactly as you said correctly, this is a local maximum, but that behavior going down and going up is a behavior of a local minimum. So it is important to know that when you are using the first derivative test, you can only apply it for continuous functions. If the function is not continuous, it could be piecewise continuous. So then you can consider it at any interval to see what happens. So you have to do it case by case. But weird continuities, so that there is no theorem, a specific theorem for them. Okay, so that's what's important. I forgot to mention. Of course, I have written it very precisely in the notes, but if you want to use the first derivative test, you have to always check that if the function is continuous or not. And if it is piecewise continuous, it means it is not totally continuous, but it is continuous on each interval, then you have to apply this rule on each piece. Yes? Okay, so now let us go here. The question is the same question, so we want to do it. So the first thing we need to do is find the domain. What's the domain here?
X is greater than 2.
No, the domain of the whole function. The function f is R again, because it is defined in this way for a smaller than or equal to 2 numbers and greater than 2. So it's defined for every number. And there are, of course, no limitations in the way that the function is defined. Okay, now if you want to follow the algorithm, you have to calculate the derivative. So, if the if you want to calculate the derivative, you have to be careful here. If x is strictly less than 2, then I know what to do. Yes, the derivative is 2x minus 2, but don't write x is less than or equal to 2. For the time being, you have to keep it less than 2. Yes, because when you want to differentiate at 2, then you have to consider sometimes x approaches to 2 from the left. This will be the rule. And if it approaches to 2 from the right, the other one will be the rule. So you have to be careful when x is equal to 2. But if x is strictly less than 2, you are on the safe side. The function is this one. It doesn't matter in which direction you are approaching. For example, if this is 2, and you are a little bit smaller, even if you are smaller than 2 here, but a little bit even, it doesn't matter. So you can approach from right to left, and still you are on the left side of 2. Okay, so that's not something that we have to be careful. Similarly, you don't have to be careful here. Yes, that's also correct. But you have to be careful what happens exactly at 2. Okay, so it means that I am not still done with my derivative. I know the derivative is this if x is less than 2 strictly, and this one if x is greater than 2 strictly, but I still need to know what happens exactly at 2. The first thing that you check is continuity. Because if you are lucky and that is not continuous, you can immediately jump to the conclusion that the function is not differentiable either. Okay, so let us check. Is this function continuous? You can do it quickly in your head. Yes, if you put 2 here, it becomes 4 minus 4, 0. If you put 2 here, so it means that I am taking the limit from the left and from the right. If I put 2 here, it becomes 8, 36 minus 36, that's also 0. So yes, this function is continuous as 2, okay? So I cannot immediately jump to the conclusion that the function is differentiable, because the other way around does not work. If it was not continuous, I could conclude that it's not differentiable. So this means that I have to go to the definition of the derivative at 2. So I have to calculate f prime plus at 2. This is the limit of f of x minus f of 2 divided by x minus 2, x goes to 2 from the right. So this means that this is the limit, x minus 2, copy and paste. F of 2 is 0, yes, but f of x, because x goes to 2 from the right, I choose this one. Yes, x goes to 2 from the right hand side. So I can, yeah, it's a little bit problematic if I want to use factorization, but we learned something yesterday to calculate 0 over 0 limits, yes? Yes, so this I can use Hobbitor's rule. Yes, Hobbitor's rule number 1. So if I take that one, the derivative of the denominator is 1, the derivative of the numerator is 3x squared minus 18, and x goes to 2 from the right side. So if I calculate that one, it is a minus 6. And then I calculate f negative at 2, so this will be the limit f of x minus f of 2 divided by x minus 2, x goes to 2 from the left this time. This one is the same, 0. This one, I have to choose the first one. You can also use Hobbitor's rule, but this is extremely simple. If I factor x out, x minus 2's are gone, x is left, x goes to 2, so it becomes 2. And then you see that the left and the right derivatives are not equal, so what can I conclude? So this means that f is not differentiable at x equals to 2. This is the conclusion. So it means that this is a good derivative. This is complete.
Yeah, just plug in 2.
Yes?
Can we not just differentiate the expressions without limits and see whether they are equal or not?
Yes, you can, but there is a theorem, it is not mentioned in this course, so I'm not sure that if you use that, because there is a theorem that you can use using mean value theorem. you'd calculate this and take the limit of this one. If the function is continuous, which it is in this case. If I send x to 2 from the left, it becomes 4 minus 2 is 2. And if I send x to 2 from the right, it becomes minus 6. But in this course, because in this book we haven't that theorem, so don't use it in the exam. Yes, but that's, in technically speaking, that's correct. But you have to make sure that your function is continuous. So if your function is continuous, what you said is correct. In case if you want to calculate the right-hand side limit, you can take the derivative and calculate the limit when x goes to a from the right. But this theorem is not mentioned in the book, so I think you're not allowed to use it. But anyway, it's not very lengthy, so you can calculate. Okay, now this is the best derivative I have. I know what happens for my derivative if x is strictly less than 2, what happens if it is strictly greater than 2. And I also know that there is no way I can talk about the derivative at 2 because I showed that derivative at 2 does not exist. Okay, so let us now go back to critical points. So, critical points. So, what are critical points? The critical points are the points at which the derivative is equal to 0. But my derivative has 2 rules for it, so I have to consider both. But there is also a domain of applicability, so be careful about that domain as well. So I put the first rule. So I would say that if x is greater than 2, less than 2, I put this derivative to x minus this rule of my derivative equal to 0 and try to solve it. This becomes 1. But be careful, is this acceptable? You have to check it under 2 conditions. First of all, it should be in your domain, which of course it is, and it should also satisfy this condition. Because the derivative follows this rule only if x is less than 2, and I am getting 1. 1 is really less than 2, so I accept it. This is one critical point. Yes? But there is another scenario here. If x is greater than 2, then I have to put this rule equal to 0. Critical points, let me write it here for you. Critical points means the derivative is equal to 0. So this means that 3x squared minus 18 is equal to 0. This means that x squared is
Plus minus 3.
Plus minus 3 was my intention, but it is not, is it?
Oh yeah, I root 6.
Yeah, it is a very bad number, unfortunately. So when I was designing the question, I was trying to make it so simple, but it is not apparently, yes. Anyway, so this is plus or minus the square root of 6. Yes. But then, from the domain point of view, I don't have any problems, but this I should also satisfy. So one of them is not acceptable. The square root of 6 is also beyond 2, so that's acceptable. So this means that considering this, we have only one of them, yes? X equals to square root of 6. So how many critical points I have? I have 2 critical points. The derivative exists and is equal to 0. It means what? It means that if someone draws the graph of this function, you will see that at 2 points, the derivative, the tangent line is horizontal. But still we don't know if this one is minimum or maximum or whatever, or is a Taylor's point or not. Yes.
So undefined points are critical, but when the derivative doesn't exist or not.
Yes. These are the words that we want to differentiate this. When we say a critical point, it means the derivative is 0. When we say a singular point, it means the derivative does not exist. Okay? And I gave this example intentionally because you see that here, when I talked about singular points, I realized that, okay, this is my derivative. I demand that it is not defined. So I put the derivative equal to 0 by hand. But this derivative appears to be defined everywhere, except, as this example, this calculation shows, at 2. So the derivative does not exist at 2. So 2 is the only critical point. Okay? So, sorry, singular point. Singular points. So, the points at which f prime of x does not exist. So, but which point is that? Because my derivative is defined everywhere, before 2, after 2, but it is not defined exactly at 2. So 2 is the only singular point. So therefore x is equal to 2 is the only singular. And endpoints, we don't have endpoints, yes? No endpoints. Okay, so now we want to know which one is which. So what we are supposed to do, we need to set up a table. So we have x, f prime, and f. X goes from minus infinity to infinity. So there are some candidates that I collect them when I was doing this calculation, 3 of them. 1, square root of 6, and 2. Yes? Okay, so which one I have to write first? This one is the smallest one. I write first, and then 2, and then a square root of 6. Yes? Okay, at 1 and a square root of 6, the derivative is indeed equal to 0. So the derivative is 0 here, the derivative is 0 there. But at 2, the derivative is undefined. Okay, so let us skip this calculation because that's simple. You have to calculate f of 1, f of 2 if you want to. Of course, as far as the character and this example is concerned, you really don't need to calculate those numbers. Okay, now let us decide about the sign of the derivative. Let us assume that x is any number less than 1. So what do you think will happen for my derivative? This is my derivative. If x is less than 1, I have to use this rule. So forget about this one. And then if x is less than 1, this becomes negative. Is that right? So that is negative. Now pick any number between 1 and 2. Any number it should be. Still, you are below 2. So if you are below 2, the derivative still follows the same rule. But this time, x is greater than 1. So what happens to this? It becomes positive. Now, any number between 2 and square root of 6, you are above 2. When you are above 2, you are not allowed to use this, you have to use this one. And you are above 2, but below square root of 6. So this becomes what? Negative. Yes? Because exactly at the square root of 6, it becomes positive. So it's negative there. And now if you go beyond square root of 6, because still you are beyond 2, you have to use the same rule. But because you are greater than a square root of 6, this becomes positive. Yes? And then it becomes decreasing, increasing, decreasing, increasing. Okay, now everything becomes very clear. So what type of, this one is what? Local. So if I want to write like this, local mean. What are the local mean points? I have 2 of them. X equals to 1. And then x equals to square root of 6. And local max. Do I have a local max? Yes. X equals to 2. But I know that at this point too, I'm not sure if you draw the graph of this one, might be you get something because you have 2 minimum. Yes. And then at that point, you don't have that. So it means that something like this. You have 2 graphs on the left and the right. So you have 2 minimums, one coming from this rule, the other one coming from that rule, and then you have a sharp point, which is your maximum. I'm not sure, but this is something around that. Yes?
If a function is a constant function, is every point an extreme point?
Yes.
So every point is both a minimum and maximum?
And maximum.
Okay.
Yes. I think this is the standard in the book as well.
Yeah.
Okay, any questions? Understandable? So we can have a break now, and then we can continue.